During the Environmental Quality Sampling course, you've been learning how to properly collect samples and fill out the chain of custody. Now we're going to follow what happens to these samples when they arrive at the laboratory. These soil samples are to be analyzed for lead. We collected, sieved, and homogenized them in the field. The sieving and homogenization procedures were specified in our field sampling plan, which was reviewed and concurred with by the appropriate regulatory agencies for this project. It is important to note that the soil collection procedures will differ with each project, depending on the decisions to be made and applicable regulations. For example, some states do not allow soil sample homogenization. This groundwater sample is to be analyzed for the volatile organic compounds benzene, toluene, and xylene. Now, all these samples are listed on this chain of custody form. Since these are routine compliance samples, we're following a typical custodial rather than more stringent legal chain of custody procedures. Before placing the original chain of custody form in the cooler, we make a photocopy for our records. As part of the hazardous waste determination, these samples will undergo a toxicity characteristic leaching procedure, or TCLP. The analytes of concern in this waste stream are trichloroethylene and cadmium. Since these samples have a much higher level of hazardous constituents than either our soil or groundwater samples, we are shipping them in a separate container. When packing the cooler chest, we put the sample bottles in only one layer. We don't stack the bottles on top of each other. We use plenty of ice, regular ice, not blue ice or dry ice. Now we just have to seal the chest and transport it to the laboratory. If transport by a commercial overnight delivery service is available, their paperwork satisfies the chain of custody requirements. Be sure to keep copies of your records and to check and ensure that the samples were delivered on time. But in our case, since our lab is nearby, we're going to transport them to the lab ourselves. The first thing the lab will do is check in the samples according to the lab-specific procedures. In this case, we note whether the container is sealed upon arrival, and then open the chest and check the temperature. Then each sample is inspected. At this point, the laboratory would verify preservation of the samples if applicable. Preservation of volatile organic samples is verified at the time of analysis, not receipt. The information on each sample container is compared with the information on the chain of custody form. You need to have established a working relationship with your lab so that if there are any discrepancies, the lab knows whom to contact. Response to inquiries regarding discrepancies is time sensitive, since most often a laboratory's procedure calls for them to place analysis of the samples on hold until the discrepancies are resolved. This can jeopardize the laboratory's ability to meet holding times and compromise the data usability. Upon receipt of the sample, the laboratory custodian signs the chain of custody form, makes copies of it for the laboratory records, and returns it to the owner of the samples. If we'd shipped the samples by commercial carrier, the lab would have faxed the chain of custody. Next, a laboratory identification number is assigned to each sample by the Laboratory Information Management System, or LIMS. This lab barcodes each sample container. Then the sample containers are securely stored in this refrigerator. Samples for the volatile organic compounds, in this case the samples in the VOA vials, are stored in a separate refrigerator to prevent cross-contamination. The samples will be analyzed in two different areas in the lab. Since the soil samples are to be analyzed for inorganic parameters, they will be sent to the inorganic section of the lab. The groundwater samples will be analyzed for organic compounds, so they will go to the organic laboratory. Due to the nature of volatile organic compounds, the organic laboratory has a positive pressure air handling system. This helps to prevent cross-contamination from the other areas caused by the use of solvents such as methanol, acetone, and methylene chloride, which could be analytes of concern. The hazardous waste samples will go to the TCLP lab. Here in the inorganic laboratory, various wet chemistry tests are performed, such as pH, flash point, oil and grease, ammonia, and biochemical oxygen demand, or BOD. In addition, metal samples may be digested in this area. Our soil samples will be analyzed for lead using this inductively coupled plasma mass spectrometer, or ICP instrument. Other instruments that could be used to analyze for lead are inductively coupled plasma mass spectrometer, ICP atomic emissions, atomic absorption known as AA, or graphic furnace atomic absorption known as GFAA. AA and GFAA are older technologies that can analyze for only one metal at a time. They can be economical if only one metal is being analyzed for. In an ICP-MS, all metals can be detected simultaneously in one analytical run. They can be the best analysis instrument to use for samples that are being analyzed for several metals. Detection limits vary by instrument type, so the project plan should ensure that the technology selected for the analysis can meet the project requirements for the sensitivity. This lab uses the ICP-MS as it has greater sensitivity and lower detection limits. For metal soil samples, 1 gram or less of the sample is used in the analysis. This is another reason why the soil handling procedure needs to be well thought out by the project manager to ensure that the laboratory analysis data will be useful for making the project-specific decisions. During transportation, samples may jostle around. The soil in the jar could be stratified as a result of the jostling. Larger particles tend to wind up at the top of the jar, while smaller particles end up at the bottom. If the chemist just scoops the soil from the top of the jar, it may not be representative of the sampling location site as a whole. In our case, we're interested in the concentrations of lead at our site for a soil of a particular grain size. Therefore, we sieved and homogenized the soil in the field. Since the grain size is the same throughout the sample, the lab does not have to homogenize the sample. If homogenization is not performed in the field, the project manager needs to review the laboratory's subsampling procedures to ensure the project needs can be met. To prepare samples for analysis, an acid or microwave digestion is performed. Acid and water are added to the digestion tube containing the samples, and the samples are heated for specific amounts of time. One aspect that's important to consider during the project planning is that the holding time for metal samples is 6 months for metals other than mercury, which has a 28-day holding time. The samples are introduced to the instrument via tubing and a peristaltic pump. Most laboratories use auto samplers for the sample introduction step. The instrument is calibrated using standards of known concentrations prior to sample analysis. The concentration of the analyte, in this case lead, is calculated from this calibration. The analyst prints out the calibration and sample results. This is referred to as raw data. The organics lab has a sample prep area, an area for analysis of semi-volatiles, and an area for volatiles analysis. Our samples are being analyzed for benzene, toluene, and xylene, which are volatiles. To avoid cross-contamination, we'll visit the volatiles laboratory first. Volatile organic samples do not need to be prepped. However, the chemical preservation is checked at the time of analysis. The holding times for chemically preserved water samples and soils are 14 days from collection to analysis. The holding time for unpreserved water samples is 7 days from collection to analysis. Approximately 1/2 to 1 milliliter of the sample is injected into the gas chromatograph mass spectrometer, or GCMS. Like the analysis for lead, the GCMS is calibrated using standards of known concentrations prior to sample analysis. The concentrations of the analytes are calculated from this calibration. One of the big differences between volatiles and semi-volatile samples is that semi-volatiles require extraction prior to analysis. Here in the semi-volatile preparation area, 1/2 to 1 liter of liquid sample is used, or 5 to 30 grams of a solid sample is used. The target analytes are extracted from the sample matrix using solvents and separatory funnels, or a technique such as solid phase extraction. The volume of final extract typically ranges from 1/2 to 5 milliliters. The holding time for most semi-volatile analytes is 14 days from collection to extraction. Then the extract holding time is typically 40 days from the start of the extraction process. Approximately 100 microliters of this extract is introduced into the instrument. To provide the information we need to make a hazardous waste determination, a TCLP or T-clip procedure will be performed on these samples. The TCLP procedure was developed to simulate landfill conditions. Over time, water and other liquids percolate through landfills, and if they absorb contaminants, this liquid leachate may pose public health and environmental risks. The TCLP test determines which of certain contaminants identified by the Environmental Protection Agency would be present in the leachate. If the concentrations present meet or exceed the regulatory limit listed on this chart, the waste becomes classified as hazardous waste. Therefore, it must be properly treated and disposed of. Since the TCLP method needs to accommodate a variety of wastes, there are several different steps that the analyst may perform depending on the chemical and physical properties of the waste. For example, wastes that contain a significant amount of solids are handled differently from wastes that are all or nearly all liquid. Specialized laboratory equipment is used for wastes that contain volatiles, and different extraction fluids are used depending on the alkalinity of the solid phase of the waste. The 5 basic steps of the TCLP are: Step 1, separation. For wastes that are liquid, meaning they contain less than 0.5% dry solid material, the waste is filtered through a 0.6 to 0.8 micron glass fiber filter. That filtered liquid is considered the TCLP extract and is used for analysis. For waste containing greater than or equal to 0.5% solids, the liquid, if any, is separated from the solid phase and stored for later analysis. The solid phase goes on to step 2, particle size reduction. The solid material may be no larger than specified limits. Otherwise, it must be crushed, cut, or ground up. Once the size limits are met, step 3, the extraction of solid material is performed. The solid material is extracted for 18 plus or minus 2 hours with an amount of extraction fluid equal to 20 times the weight of the solid phase. The extraction fluid used varies depending on the alkalinity of the solid phase of the waste. Also, a special extractor vessel is used when testing for volatile analytes. Step 4 is the final separation of the extractions from the remaining solid. In this step, the liquid extract is separated from the solid phase by filtration. If the initial liquid phase of the waste is compatible with this extract, the two are combined and analyzed together. If they are incompatible, each is analyzed separately and the results are mathematically combined. The final step, step 5, is the analysis of the TCLP extract in the inorganic and organic areas of the laboratory, depending on the target analytes. In addition to preparing and analyzing the samples it receives, a laboratory also prepares and analyzes a variety of quality control samples, including laboratory control samples, laboratory duplicates, method blanks, and matrix spikes along with the samples. The quality control samples are a measure of the laboratory's ability to meet the method and project data quality objectives. Okay. Once the samples have been analyzed and the raw data is processed, the data undergoes a 3-tier review, first by the analyst, then by a peer analyst, and finally by a data validator. The data is reviewed for accuracy, completeness, for compliance with reference methods, and for project-specific requirements. And therefore, communication with the laboratory is vital to ensure the laboratory understands your project-specific needs. The report that the lab sends you should contain the project name and site location, field sample identification number, the lab's identification number, the matrix, the date the sample was digested or extracted, the date and time the sample was analyzed, the method reference numbers, the name of the analyte or parameter, the method reporting limit that has been adjusted for volumes, weights, or dilutions, the method detection limit, the analytical result, the concentration units, the dilution factors, the percent moisture, and any relevant data qualifiers. Data qualifiers are flags that are intended to alert the end user of potential data quality issue that may impact the usability of the data. Although all labs do not use the same system, usually a lab will print a letter next to the analytical results to indicate a potential quality problem with that particular analysis. Be sure you know what system your lab is using and their definitions for each of the data qualifier flags. Examples of common data qualifiers are U for undetected at the limit of quantitation, J for estimated. The analyte was positively identified, but the concentration value is an estimate. The letter B may indicate there is a contamination in a blank quality assurance sample. Just because an analytical value is flagged doesn't mean it is automatically unusable. Each needs to be evaluated on a project-specific basis in a situation where contamination is found at levels well beyond regulatory limits. A B qualifier may not matter. On the other hand, if the values are close to regulatory limits, the fact that the value was estimated, or J flagged, could make the data unusable for project-specific decisions, such as whether or not a site needs to be cleaned up. In closing, I want to discuss the Department of Defense's quality requirements for laboratories. This manual identifies the minimum laboratory quality system requirements. For a lab to do work for the Department of Defense in support of the restoration program, it must meet these minimum standards with regard to facility, administration, training, documentation, procedures, assessment, proficiency testing, technical criteria, and reporting criteria. When selecting a laboratory, the project team should check that the laboratory's policies and procedures meet the project requirements. The project team should ensure that the laboratory has acceptable proficiency testing results for the analytes of concern. Part of the evaluation could be a site visit to the laboratory by the project team. A lab should welcome your visit to see how your samples will be handled. A visit can also develop those essential lines of communication that are vital to the project's success, as well as further clarify project requirements. I hope this laboratory tour has been enjoyable and enlightening. A laboratory is not a black box where samples go in and indisputable numbers come out. Rather, many factors affect the quality of the resulting data. Over the years, much emphasis has been placed on the quality of the analytical results. Instruments have been refined, strict calibration and standardization procedures put in place, and numerous quality control checks instituted. Recent studies have shown that less than 10% in variability in samples is due to what happens in the laboratory. Over 90% comes from what happens in the field due to sampling design and/or sample collection. Thank you for your attention. If you have any questions regarding your particular laboratory situation, please contact the Navy's Laboratory Quality Assurance Office.